All right, welcome everybody to Math with Miss Lastly. That is such a mouthful. I need to stop saying that. It is not cool, but it's what I come up with in the moment. So it is what it is. Okay, today we are starting Unit 6, which is our Analytic Trigonometry unit. This is by far, hands down, Miss Lastly's favorite unit of the entire year. Now, it kind of sucks because we're not going to do it for very long. It's only 3 weeks for you guys, and you only end up with a test at the end of, or a quiz at the end of this unit, which is unfortunate because it is kind of a fun unit. And there is more to it that we're having to cut out this year because of time constraints and everything. It doesn't matter. Anyways, starting today, day 1, we are going to be doing something called the fundamental identities. There are 14 total fundamental identities in trigonometry, and we are going to do them today. So you already kind of know some of them. There really is only a handful of new ones. Now, you might not have thought about all of them in the way that we're going to look at them, but you have seen them before, and I think the concept of them is going to be okay. Now, the reason that we are doing these fundamental identities is because we're going to use them eventually to solve equations. So our end goal for this unit is to be able to solve trigonometric equations. That means we're going to have a bunch of trig functions, an equal sign, and then something on the other side, and we're going to have to solve for the variable. That is our end goal. But before we can get there, there's a lot of stuff we have to talk about. So these identities are things that are going to help us get to solving those equations. All right. Plus, by doing these identities and starting to simplify trig expressions, we're going to get into something called proofs, which is not exactly what you had in geometry, but they're along the same lines, but not really. We're really going to hone our algebra skills to get us ready to do the solving piece. All right, so we have to learn the identities because that's how we're going to end up solving. We have to do this practice, which is a lot of algebra work. So we are going to talk about some algebra skills that you might want to go back and touch up on so that we can apply them to our trig expressions. All right, so we're going to introduce the identities. We're going to review our algebra. Yeah, that's a typo. Our algebra skills, and then we're going to do some examples of today's stuff. So let's go. Okay, so first off, our fundamental identities. So we're going to create them. You guys will also have a sheet. It is on Schoology, a PDF that has all of your identities that you will need to know on it. Now, normally I would make students memorize these identities. Unfortunately, you guys aren't going to have to memorize them because you're at home and you'll have them right there in front of you. So what's to make you memorize them? But I guarantee you these problems are easier if you're doing it from memory versus staring at a sheet of paper trying to figure out what your identities are. So my advice is, even though technically you don't have to memorize them because you'll have the sheet in front of you, you should memorize them because it's going to make your life easier when you're doing the problems. Okay, so first we're going to start by doing what's called the ratio identities. Ratio means fraction. All right, so I drew this, I didn't draw this, obviously. I copy and pasted this picture. But we have this picture of a nice right triangle. We have all the parts labeled, and all of this stuff is things that you should know. So sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. We have our triangle, we have all the parts labeled. All right, so none of that should be new stuff, okay? What we're going to do is we're going to use this basic information, it's the fundamentals, to create these different identities is what they're called. All right, it's really just, we're looking at relationships that we can make between these basic trig functions and each other. That's really what we mean by these identities. Okay, so starting with the first one, sine theta over cosine theta. This is not something that we've talked about before, but it is something that we've seen before when we figure out what it's equal to. Here's how it works. So what we're going to do is we're going to plug in sine. Sine is opposite over hypotenuse. So on the top, I'm going to replace sine with opposite over hypotenuse because that's what sine is, right? Those are the sides of the triangle that are my sine values. Divided by cosine theta. Cosine is adjacent over hypotenuse. Okay, cool. Haven't done anything too weird yet. Next, I'm going to simplify this. So I have a fraction divided by a fraction. So we're going to keep the top fraction exactly as is. we're going to flip the second fraction, and then we're going to change that division sign to multiplication. Keep, flip, change. All right, now we simplify. We can cross out hypotenuse over hypotenuse, and what we're left with is opposite over adjacent. Well, what is opposite over adjacent? Well, you look at that. It's tangent. So our first identity is sine over cosine equals tangent. All right, now we kind of have done that, right, when we were doing our unit circle, right? We said that sine is our y value, cosine is our x value, so tangent is y over x, so tangent is sine over cosine. This just showed you that it actually works with all trig functions. It doesn't have to be unit circle. All right, so no matter what triangle we have, the tangent value is always equal to the sine divided by the cosine. Kind of nice. All right, the second one, cosine over sine. I bet you can guess where this is going, but we're gonna walk through it anyways. All right, cosine is adjacent over hypotenuse divided by sine, which is opposite over hypotenuse. All right, we have a fraction divided by a fraction, so we're going to keep the first, flip the second, and change it to multiplication. All right, we can simplify out the hypotenuse piece, and now we're left with adjacent over opposite, which is cotangent. All right, so this is our second identity. Cotangent is equal to cosine over sine. And again, that is true not just on our unit circle, it's true for all triangles. Excellent. Let's move to our next section, which is our reciprocal identities. Again, these ones should be really easy. We should know these ones because we have talked about reciprocal a lot, especially when we were doing the inverse unit. I kept stressing reciprocal versus inverse. So you hopefully will know your reciprocals, all right? But hold on, we're keeping track. That's number one. That's our second identity. All right, so third identity. There's a lot, and there's 6 in this section. All right, sine, its reciprocal is 1 over cosecant. Sine equals 1 over cosecant. That is the reciprocal of sine, right? If sine is y, cosecant is 1 over y. That's number 3. Number 4. Cosine. That is equal to 1 over secant. There's no math involved with these ones. It's just what reciprocals are, right? So cosine is 1 over secant. All right, number 5. Tangent is 1 over cotangent. Bam. Now you can also go the other direction, right? So number 6 and 7 and 8. That way I don't have to keep doing it. I knew there were 6. I was just double checking before I labeled them all. All right. So if sine equals 1 over cosecant, then cosecant equals 1 over sine. If cosine equals 1 over secant, then secant equals 1 over cosine. This is what reciprocal means. All right, and then last but not least, if tangent equals 1 over cotangent, then cotangent equals 1 over tangent. All right, those are the reciprocals. All right, now we have the product identities, which are basically using the reciprocals to kind of make a product, right? Product means multiplying. All right, so number 9. Sine times cosecant. All right, well, we can do a little bit of work here, right? We'll do my equal sign below, right? So instead of just telling you what it is, I'm going to show you. So if we leave sine as is and we change cosecant to be 1 over sine, right? Because right above there, number 6, cosecant is 1 over sine. Well, that simplifies to 1, right? Because you can cancel out sine over sine and you're left with 1. So sine times cosecant equals 1, always. Number 10. All right, we're not going to do the whole steps, but it works the same way. Cosine times secant. Oops, I forgot the thetas. Bad job, Miss Lasley. Cosine theta times secant theta. Again, same situation. When you have the trig function and you multiply it by its reciprocal, it equals 1 every time. And number 11, tangent theta times cotangent theta equals 1. Again, when you have a trig function and you multiply it by its reciprocal, it equals 1 every time. All right, so that's 11. We have 3 left. There is a total of 14. Now, these first 11, to me, I feel like you probably knew these. Now, you might not have thought about tangent as being sine over cosine. You might not have ever thought about sine times cosecant equaling 1, but the concept should make sense. You've seen all the parts of these, maybe just haven't thought about them in this way before. These next ones are kind of new. These ones are new. You would not have thought about this before, but they're not hard, and they do actually make logical sense. You've just definitely not thought about them yet. All right, and they're our Pythagorean identities. All right, and you probably guessed it, it's going to deal with the Pythagorean theorem. All right, so I have here a triangle. This is a unit circle triangle. I know that because it has a hypotenuse of 1. All right, that's important, okay, because that means that we can call our x side the cosine function, and we can call our y side the sine function. All right, but we're jumping ahead a little bit. Okay, so Pythagorean identities. They're built off of the Pythagorean theorem, which, doing the Pythagorean theorem, we know that that is a squared plus b squared equals c squared, where a and b are the legs of our triangle, and c is our hypotenuse. So using the triangle that we have here, our one of our legs is our x. So we have x squared. The other leg would be y squared equals our hypotenuse squared, which is 1 squared. All right, now since this is a triangle with a hypotenuse of 1, I know that my x is equivalent to the cosine of my angle. So we'll say, I didn't put an angle in there. There's our angle theta. All right, so our x value is equal to our cosine of theta, because if we do adjacent over hypotenuse, it gives us just what, x over 1. So we know that our cosine value is our x value. So right here we have cosine theta squared. All right. And again, because we are, doing a triangle with a hypotenuse of 1, our y value is going to be equivalent to our sine of theta, right? Our y value is our sine. All right, so plugging that into my equation, I have sine theta squared equals, and then 1 squared, right, is 1. This is our first Pythagorean identity. All right, and we're going to rewrite it without the parentheses. So when you write cosine squared, it looks like this. So it's going to be cosine squared theta. So the square goes between cosine and the theta symbol. And then we have sine squared theta equals 1. So this is identity number 12. Cosine squared plus sine squared equals 1. Now, the other two are built off of this Pythagorean identity, this number 12, all right? To make them, what we're gonna do is we're gonna try and so there's 2 left, right? We know, I said there was 14, we're on 12. All right, so the next identity is gonna be to to change the cosine squared theta to a 1, all right? Now, Who knows why they wanted to do this, but they did. All right, so in order to change cosine squared theta to be a 1, algebraically, we can't like subtract cosine squared because then the cosine just goes to the other side, right? Or we can't subtract like something, so we're not subtracting. We have to multiply by something. All right, so to get cosine squared theta to turn into a 1, we have to divide it by itself, right? Cosine divided by cosine does equal 1. So what we do, so if we divide cosine squared by itself, that's then going to simplify to 1. Now, what we do to one part of the equation, we must do to all of the parts. You can't just divide something by 1. All right, so we might have to divide everything by cosine squared. All right, which brings us to identity number 13. We just simplify. Cosine squared divided by cosine squared is 1. Plus sine squared divided by cosine squared. We did that above. That's one of our identities. Sine over cosine, that's tangent. And since both sine and cosine are squared, it's going to be tangent squared. Equals 1 over cosine squared. That's one of our reciprocal identities. 1 over cosine equals secant. So 1 over cosine squared equals secant squared. So there's identity number 13. All right, to get the 14th one, instead of dividing to make cosine equal to 1, we're going to divide to make sine equal 1. So we're going to start with this same number 12, cosine squared theta plus sine squared theta equals 1. But now what we're going to do is we're going to try and get rid of sine. So we're going to divide to get sine to be 1. So we divide by sine squared. But we can't just divide one piece. We have to do it to everything because it's an equation. There's an equal sign, so I have to be equal. All right, so then number 14, we just simplify. All right, cosine squared over sine squared, that is cotangent squared theta plus sine squared over sine squared is 1 equals 1 over sine squared is cosecant squared theta. And that's it. Those are your fundamental identities. So there's a total of 14. Yes, in theory, you should memorize these 14 identities. All right, most of them I think you should probably already know just because of how much trig we've done so far. Those last 3 a little bit different, but you will use them all the time, so you should definitely memorize them. Okay, next thing we're going to talk about is the skills that we're going to be using a lot. Our algebra skills that we're going to be using all the time in this unit. The first one is how to add and subtract fractions. We are going to be doing a lot of adding and subtracting fractions, which means you need to be able to make a common denominator. So add/subtracting fractions. You need to be able to make a common denominator. All right, that is skill number 1. And if you look at our examples down there, very first problem, number 1, you need to be able to make a common denominator. Algebra skill numero dos, taking a GCF out. So factoring GCF. GCF stands for greatest common factor. It's when you pull something out that both terms have in common. You need to be able to do that. You will use it a lot. Speaking of factoring, there's a lot of factoring you're going to have to be good at. Number 3, factoring difference of squares. All right, if you forgot what that means, Google it. You're going to know how to have to do a factoring with difference of squares. The fourth one you're going to have to be able to do is just box method factoring. Box max method. All right, we're going to do a lot of factoring. As you can see, we got 3 types of factoring here. We're going to be doing all the factoring. All right, and then last but not least, this is you're going to use other skills, but this is the next one that shows up a lot. And this one is complex fractions. So when you have a fraction divided by another fraction and you got to flip and multiply. So the 5th one, complex fractions. All right, you're going to use those a lot also. All right, so those are the top 5. If I were to give like an honorable mention, so if I were to make a 6th one, this isn't used as much, but it definitely is going to come up when we start doing a little bit more challenging problems, and that's multiplying by a conjugate. All right, multiplying by a conjugate. All right, we are going to have to do that a lot. So a conjugate is, for instance, if you have on the denominator 1 plus x, the conjugate would be 1 minus x. And you guys did that when you were working with imaginary numbers last year in Algebra 2. So if you have an imaginary number in the denominator of a fraction, you can't leave it there. You have to get rid of it. And you do that by multiplying by the conjugate. So that's something that you won't do all the time, but you will definitely see us do in this class. So my advice is to either, if any of these topics seem unfamiliar to you, to email me and ask for example problems on how to do these using just normal algebra. And that way you'll be able to do it when we're doing our trig stuff. All right, so if any of these concepts seems very unfamiliar to you and you think you need extra practice, let me know and I will send you extra practice. It's gonna be with variables, not with trig stuff. That way you can kind of brush up, and that way when we do it with trig stuff, you can get better at it. But starting today, these are skills you're gonna need to know how to do. It's a lot of algebra to do this part of the school year. Okay, so now we're going to do some examples. So this is what your homework is going to be tonight. You're not solving yet. You're not doing proofs yet. What you're going to do is you're just simplifying trig expressions. You can use algebra skills and you can use your 14 identities. All right. The goal is to get it down to just one trig function using appropriate math. All right, no makeup math, don't do anything dumb, all right? You're using just real math rules and you're trying to get both of these examples, we're gonna simplify to just one trig function. It seems impossible, but we're gonna do it. All right, so starting with number 1. All right, first thing I notice here is that I have a fraction minus a fraction. And if my goal is to put this into just one trig function, I need to make a common denominator so that I have just one fraction. To do that, I need to multiply the first fraction by sine theta over sine theta. I need to multiply the second one by cosine over cosine. So multiply by sine theta, multiply by cosine theta over cosine theta. All right, now I'm just going to do that. So I have sine theta times cosecant theta minus cosine theta times cosine theta all over cosine theta sine theta. All right. Now, this might look worse, but it's not, because some of you probably are already looking at this. You can simplify some stuff. All right. Sine times cosecant, that's an identity. Sine times cosecant simplifies to 1. So this becomes 1 minus cosine times cosine. Well, anything times itself is squared. So this is cosine squared over cosine theta times sine theta. All right, cosine times sine is nothing. Cosine divided by sine, that's something, but cosine times sine is nothing, so we just leave it. Now, this right here should start to look familiar. 1 minus cosine squared. Well, you don't have a 1 minus cosine squared, but if you scroll through your identities, right, you do have cosine squared plus sine squared equals 1. If we were to say, I don't know, subtract cosine from both sides of number 12, our identities, wouldn't that give us what we have in our thing, right? So if we were to, oops, I didn't mean to have the highlighter. If we were to take this and we were to say subtract cosine from both sides, oh, my head is in the way. It's okay, I'll go down, right? We would have sine squared theta equals 1 minus cosine squared theta, right? All I did was subtract cosine squared from both sides. Come on, there we go. All I did was subtract cosine from both sides, all right? So I know that 1 minus cosine squared equals sine squared. So I can go back over here and I can say, okay, 1 minus cosine squared, well, that's just sine squared. So my next step, I replace 1 minus cosine squared with sine squared over cosine theta, sine theta. Now we have sine squared over sine. We can simplify that. All of this is multiplying. So we can say, we can rewrite it. Sometimes people like to rewrite this. Sine squared is sine times sine over cosine times sine. Cancel, cancel. So rewriting this again, we have sine theta over cosine theta. And guess what? That's an identity. Sine theta over cosine theta is tangent theta. So that original statement is equivalent to the tangent of theta. That's simplifying trig expressions. All right, we're going to do one more, but let's just hit some key pieces here. These are the skills that I used. I created a common denominator. I used sine times cosecant, so I used a reciprocal identity. I also did 1 minus cosine squared, which is a Pythagorean identity. And then I simplified my fraction, so I got rid of sine over sine. And then I used my ratio identity, sine over cosine, to turn it into tangent. There's a lot of pieces that I used to do this problem. This is an easy problem. We will do a lot of practice. Okay, number 2. All right, I have secant plus 1 times secant minus 1. So the first thing I need to do is I need to multiply. So we're going to FOIL, first, outer, inner, last, or however you do it. Secant times secant, that's secant squared. Secant times minus 1 is minus secant. 1 plus secant is, positive 1 times secant is positive secant, and then 1 times negative 1 is negative 1. Secant, negative, and plus cancel out, so what we're left with is secant squared x minus 1. All right, well, that's not an identity, but it's close to one. So if we take a little journey, key thing here is if you see something squared and there's a 1 with it, it's probably one of these Pythagorean identities. All right, so we have secant squared minus 1. Well, look at number 13. Number 13 has a secant squared and it has a 1, but the 1 is in the wrong spot. So guess what we're going to do? We're going to subtract it from both sides. And you get tangent squared tangent squared theta equals secant squared theta minus 1. So we can go back down to our problem, and secant squared theta minus 1 is the same as secant squared x minus 1, and we know that that is equivalent to tangent squared theta. And that's as far as we can go, because we now have it down to one trig expression. All right, maybe that was a little easier than the first one. I definitely want to make sure we did the first one because creating that common denominator is a skill that we will use all the time when we're doing our trig expressions and then when we get into trig equations. But yeah, so just to recap, I know this seems kind of ridiculous that we're doing this, but think about the benefits this has when we're trying to solve an equation. If we're looking at a problem like number 2, and we have this whole piece equals some number. If we can simplify it down to tangent squared equal to some number, that's so much easier to solve than these two binomials times each other. Same thing as number 1. Number 1 has cosecants, cosines, sines, like it's got 3 different trig functions. Imagine if we had that equal to something. That's a lot. Instead, by simplifying, we got it down to just tangent of theta. And if we had it equal to some number on the other side, that's a doable problem. Then we just need to do inverse tangent of whatever the number is on the other side. So I know this seems tedious and it seems like a lot of work, but that's how we're going to be solving. So we need to be able to do the simplifying so that we can do the last piece, which is going to be eventually to solve. We're not there yet. We're just at the simplifying stage. All right, so use this to do your homework. We will definitely be going over a lot of different examples in class on the next time I see you, but see if you can use these fundamental identities and these 2 examples to do the simplifying that you have on your homework. Remember, the goal is when you're simplifying to get it down to just one trig function. That's how you know you've done it. Hopefully, you've done it right. All right, that's it for today. I'll see you next time. Bye.